Welcome to Lesson 5 of Module 2 on hyperparameter tuning. Today, we will cover hyperparameter in ML algorithms, setting your hyperparameters and validation methods. Let's start by discussing hyperparameters in ML algorithms. Hyperparameters are parameters that affect the performance and structure of an ML algorithm. You specify hyperparameters when you configure the code before training. You can think of them as options or settings for model training jobs. Hyperparameters are not the same as the ML model's parameters, for example, weights that are attached to each model's features, which are learned from the data. Different choices of hyperparameters could lead to different model performance metrics. However, knowing exactly which values would maximize learning, and therefore model performance, is challenging. Typically, you start at a random value and iterate through adjustments as you see what effect the parameters have. This process can be long depending on how many hyperparameters your model has and how long it takes to train. Some examples include the number of neighbors and k-nearest neighbors, the max depth in decision trees, the number of estimators in random forest and ensemble bagging, and the learning rate in gradient descent. Hyperparameters and parameters are two different concepts in ML, although they are often mistaken to be the same. You can consider hyperparameters as the configurations or settings for the ML algorithm or model. However, parameters are values that loosely embody the rules that the ML algorithm seeks to learn from the data. You set hyperparameter values based on heuristics prior to training. Parameters, such as weights, are learned during model training. Some common hyperparameters for linear regression are learning rate for gradient descent and coefficient for regularizing penalty term. Parameters for a linear regression model are weights and bias values. The learning rate hyperparameter has an impact on how long it takes the model to converge. When this hyperparameter is too small or too large, the model might never converge. By finding the optimal learning rate, you can reduce the time to train a model, which also reduces the compute cost for training. You have seen several models, such as neural networks, k-nearest neighbors, KNN, decision trees, and logistic regression. As the designer, it's confusing to know exactly which model would be most appropriate for a dataset. In addition, each model has a set of hyperparameters, as some examples are given in the slide. With all these choices of models and their corresponding hyperparameters, how should you select a model that yields the best performance? As ML models get more sophisticated, you need to make more architectural decisions. Several methods are available to tune the hyperparameters to improve model performance. The search for the best combination of hyperparameters is called hyperparameter tuning. This process involves adjusting one or more hyperparameters to improve a desired performance metric. Any good ML project relies on knowing what the best values are to use for the hyperparameters of a given algorithm on a given dataset. All ML libraries and ML platforms have a few choices or implementations of hyperparameter tuning, also called hyperparameter optimization. If you don't have separate training and test datasets, make sure that you split your data into training and test datasets. Create a set of data that is not used during the training and validation phases. You will use this dataset at the end of the process to test model performance. You can then estimate the model error by using the test dataset. Even then, model building involves some experimentation or tuning, for example, which ML hyperparameters and algorithm parameters to choose. With the test set separated, you need a way to validate the model during training. One option is to further divide the training dataset into a training set and a validation set. You proceed as before, but you use the validation set to validate the performance and adjust the algorithm's hyperparameters, selecting the model that performs best on this validation set. You can train this best model on the full training set, including the validation set, for the last time. This gives you the final model, which you can evaluate on the test set to get a final good estimate of the generalization error. How should you split your dataset into training, validation, and test sets? You could simply slice your dataset or use library functions to split the data. One library is train_test_split from scikit-learn. It's a good practice to shuffle the dataset before splitting to avoid bias in the resulting sets. How much of the original dataset to keep for the training and test sets mainly depends on the total number of samples, rows, in your data. Like many other things in ML, the train-test validation split ratio is quite specific to your case, dataset, or algorithm of choice. Consider the following questions to help you choose the split ratio. Does your choice of algorithm need more training data to learn? Does your choice of algorithm have many hyperparameters to tune? Do you have enough of data? You can experiment with different split ratios to find the best data split. After a while, you might get a sense for what works best for your particular case. If both the validation and test sets are used to evaluate the model's generalization performance, why do you need two different subsets? Even though the validation set samples are not used to train the model, the evaluation is used to compare multiple models or hyperparameters. Therefore, the validation score plays a role in selecting the model and tuning the hyperparameters, which makes the evaluation biased. For a truly unbiased evaluation, you would need a dataset that hasn't been observed during training, or model, or hyperparameter selection. That is why a separate test set is used. The samples of the test set are strictly used to evaluate the trained model with hyperparameters that were selected by the validation set. It is the final evaluation of the trained model. Now, we will discuss validation methods. K-fold cross-validation is a crucial statistical method used to assess how well a machine learning model will generalize to independent data. In this example with k equals 5, here's how the process works. First, we begin by dividing our complete dataset into 5 equal size, non-overlapping segments or folds. Then, we perform an iterative process that consists of 5 rounds. In each round, we reserve one fold as a validation set, shown in blue in the diagram. We use the remaining 4 folds as training data, shown in white. We train our model on these 4 folds. We test the model's performance on the reserved validation fold. Finally, we record the performance metric for that round. This process repeats 5 times, with each fold taking a turn as the validation set. As shown in the diagram, we get 5 different metrics, metric 1 through metric 5, one from each iteration. The beauty of this approach is that by the end, every data point has served both as training and validation data. Finally, we combine or average these 5 performance metrics to get a more robust estimate of how well our model performs. This method is particularly valuable because it makes efficient use of limited data, provides a more reliable estimate of model performance, helps prevent overfitting, and gives us insight into how well our model generalizes to unseen data. The final average result gives us a more reliable indication of how our model might perform on new, unseen data compared to using a single trained test split. Grid search is a brute force approach to hyperparameter tuning in machine learning models. It involves searching over all possible combinations of hyperparameter values to find the optimal configuration. For example, when tuning a decision tree model, the hyperparameters could include the maximum depth of the tree and the minimum number of samples required at each leaf node. The grid search process would evaluate the model's performance for every combination of these hyperparameter values from a predefined set. The slide illustrates this concept using a decision tree example with 2 hyperparameters, max_depth and min_samples_leaf. The param_grid dictionary defines the values to be tested for each hyperparameter, with max_depth ranging from 5 to 250, and min_samples_leaf ranging from 15 to 35. The total number of hyperparameter combinations is calculated as the product of the number of values for each hyperparameter, which in this case is 5 times 5 equals 25. The slide shows a few examples of these combinations, such as 5, 15, 5, 20, 5, 25, 10, 15, and so on. The grid search approach is visualized using a grid-like structure, where each node represents a specific hyperparameter combination. The model is trained and evaluated for each combination, and the configuration that yields the best performance metric is selected as the optimal set of hyperparameters. Grid search is a straightforward approach to hyperparameter tuning, with several advantages. It is easy to implement and provides an exhaustive search, considering all possibilities within the specified range of hyperparameter values. Additionally, grid search can be parallelized, allowing for efficient exploration of the search space. However, grid search also has some drawbacks. It discretizes continuous variables, which may lead to suboptimal solutions. Furthermore, The computational cost grows exponentially with the number of hyperparameters, making it impractical for high-dimensional problems. Lastly, grid search is not a smart approach, as it does not utilize information from previous evaluations to guide the selection of subsequent hyperparameter values. To address these limitations, more advanced techniques like random search, Bayesian optimization, and gradient-based methods have been developed. These methods aim to intelligently explore the search space, converging to optimal solutions more efficiently than grid search, especially in high-dimensional spaces. Randomized search is an alternative approach to hyperparameter tuning. Instead of exhaustively searching the entire hyperparameter space like grid search, it chooses a fixed number of random combinations of hyperparameter values and only tries those. This can be more efficient, especially for high-dimensional problems where grid search becomes computationally expensive. Randomized search also has the ability to sample from distributions if at least one parameter is given as a distribution, using sampling with replacement. For example, in the case of a decision tree, the hyperparameters could include the maximum depth, which can be specified as a list of values, and the minimum number of samples required at a leaf node, which can be given as a uniform distribution. The slide illustrates how randomized search randomly selects combinations of hyperparameter values from the specified ranges or distributions. Randomized search offers several advantages. It is scalable with respect to the number of hyperparameters, meaning it can handle problems with many hyperparameters effectively. It is also compatible with continuous variables, allowing hyperparameters to take on any value within a specified range. Additionally, randomized search can easily try more combinations of hyperparameter values, and the evaluations can be computed in parallel for increased efficiency. However, randomized search has some drawbacks. Choosing the best sampling distribution for the hyperparameters might not be trivial, and the approach is not smart in the sense that previous evaluations are not used to guide the selection of the next set of values to try. It simply samples randomly from the specified distributions or ranges without learning from previous iterations. Bayesian search is an approach for hyperparameter optimization that keeps track of previous hyperparameter evaluations and builds a probabilistic model. It balances exploration, which involves exploring the whole sample space, and exploitation, which focuses on exploiting promising areas. This technique aims to intelligently navigate the search space by learning from previous evaluations, unlike randomized search which samples blindly. Amazon SageMaker, a machine learning platform, uses Bayesian search for hyperparameter optimization. By maintaining a probabilistic model of the hyperparameter space, Bayesian search can make informed decisions about which hyperparameter values to try next, potentially leading to more efficient optimization compared to randomized approaches. The slide compares Bayesian search and grid search for optimizing the choice of hyperparameters in machine learning models. Instead of randomly choosing the next set of hyperparameters, Bayesian search is likely to reach optimal hyperparameters faster than grid search or random search. This is because Bayesian search intelligently selects the next set of hyperparameters to evaluate based on previous evaluations, rather than blindly sampling the search space. The graph shows that Bayesian search achieves higher scores more quickly compared to grid search over multiple iterations. Additionally, Bayesian search is partially parallelizable, which can further improve its efficiency. Overall, the slide highlights the advantages of Bayesian search as a more effective and efficient approach for hyperparameter optimization compared to traditional grid search methods. Bayesian search offers several advantages over traditional grid search methods for hyperparameter optimization. It is highly scalable, capable of handling a large number of hyperparameters efficiently. Additionally, Bayesian search can accommodate continuous valued hyperparameters, which is often necessary for certain models and algorithms. One of its key strengths is its ability to leverage previous evaluations to intelligently select the next set of hyperparameter values, making it smarter and faster than grid search, which blindly samples the search space. However, Bayesian search also has some limitations. While it is partially parallelizable, it cannot be fully parallelized, which may impact its efficiency in certain scenarios. Furthermore, there are still some settings known as hyperparameters that the designer needs to choose, which can influence the performance of the Bayesian search process. Overall, Bayesian search offers a more effective and efficient approach to hyperparameter optimization compared to grid search, particularly for complex models with many hyperparameters. However, it is important to carefully consider the trade-offs and choose the appropriate method based on the specific requirements of the problem at hand. The slide introduces 3 hyperparameter tuning methods that can be used with the fit and predict functions in scikit-learn. The first method is grid search, which involves specifying a grid of hyperparameter values to search over. The grid search function is used to perform this search, taking an estimator object, the parameter grid, and optionally a scoring metric. The second method is random search, which randomly samples hyperparameter values from specified distributions. The randomized search function is used for this, taking an estimator, the parameter distributions, the number of iterations, and optionally a scoring metric. The third method is Bayesian search, which uses a Bayesian optimization approach to intelligently search the hyperparameter space. The Bayes search function is used, taking an estimator, the search spaces for the hyperparameters, the number of iterations, and optionally a scoring metric. These methods provide different approaches to hyperparameter tuning, with grid search being an exhaustive search, random search being a randomized approach, and Bayesian search using a more intelligent and efficient optimization technique. The choice of method depends on the complexity of the problem, the number of hyperparameters, and the available computational resources. This lesson covered how to select hyperparameters to improve a model's performance. In the next lesson, you will learn how to combine individual ML models to build stronger predictors. Combining multiple models can often lead to better performance than any single model alone. Some common ensemble techniques include bagging, boosting, and stacking. We will explore the strengths and weaknesses of these different ensemble approaches, as well as best practices for creating effective ensemble models tailored to your specific prediction tasks. Thank you for your participation in this course. We've covered a lot of important machine learning concepts and techniques. As we move forward, we'll dive deeper into advanced ensemble modeling approaches that can further boost predictive performance by combining multiple models. I'm excited to explore the strengths and trade-offs of techniques like bagging, boosting, and stacking with all of you. By mastering these ensemble methods, you'll gain powerful tools for tackling complex prediction problems across diverse domains. Our goal is to equip you with cutting-edge skills to build highly accurate and robust predictive systems. Let's continue learning and growing together.